Myself, Maurya Satish. Roll number is 209-518-3329. Computer Science and Information Technology Department. Subject is Design and Analysis of Algorithm. Subject code is ACS C13 AAT Video Concept. AAT concept is a lower and upper bound theory. First of all, we are going to discuss about its introduction and lower bound theory and its examples, upper bound theory and its examples. Introduction. The lower and upper bound theory provides a way to find the lowest complexity algorithm to solve a problem with. Before understanding the theory, first let's have a brief look at how lower and upper bounds are. Lower bound theory concept is based upon the calculation of minimum time that is required to execute an algorithm is known as lower bound theory or base bound theory. Lower bound theory. Lower bound theory concept is based upon the calculation of minimum time that is required to execute an algorithm is known as lower bound theory or base bound theory. Lower bound theory uses a number of methods, techniques to find out the lower bound. Concept or aim. The main aim is to calculate a minimum number of comparisons required to execute an algorithm. Techniques. The techniques which are used by lower bound theory are comparisons tree, oracle and adversary arguments, state space method, comparison tree. In comparison sort, we use only comparisons between elements to gain order information about an input sequence A1, A2, A3, so on till A1. Given AI, AJ from A1, A2, A3, so on till AN, we perform one of the comparisons. AI is less than AJ. AI is less than or equal to AJ. AI is greater than AJ. AI is greater than or equal to AJ. AI equal to AJ. To determine their relative order, if we assume all the elements are distinct, then we just need to consider AI less than or equal to AJ is excluded, and less than or equal to greater than or equal to less than greater than are equivalent. Consider sorting three numbers A1, A2, and A3. There are 3 factorial, that is 6 possible combinations. A1, A2, A3, A1, A3, A2, A2, A1, A3, A2, A3, A1, A3, A1, A2, A3, A2, A1. The comparisons based on algorithm defines a decision tree. A decision tree is a fully binary tree that shows the comparisons between events that are executed by an appropriate sorting algorithm operating on an input of a given size, control, data, movement, and all other conditions. Algorithm control, data movement, and all other conditions of an algorithm are ignored. In a decision tree, there will be an array of length n. So total leaves will be n factorial, that is total number of comparisons. If tree height is h, then surely n factorial is greater than or equal to 2 power n. Tree will be binary. Taking an example of comparison of A1, A2, and A3, left subtree will be true condition, that is AI is greater than or equal to AJ, and right subtree will be false condition, that is AI is less than AJ. Decision tree. As you can see, A1 is greater than or equal to A2. Yes. If A2 is less than or A1, then it is no. It goes to right subtree, and this is go to left subtree. And here the comparisons between A1 and A3 and A2 and A3 moves on till we get an order. Yes, if 1, 2, 3, A2 is greater than A3, that is A1, A2, A3. No, if A1 is less than or equal to A3, that is 1, 3, 3. A3 is less than A1, that is no. A1, A3, A2. Yes. If A1 is less than or equal to A3. No, if A2 is greater than or equal to A3, then it will go 2, 3, 1. And if no, 3, 2, 1. So from above, we got n factorial is greater than or equal to 2 comma n. Taking log on both sides, we get log n factorial is equal to h log 2, n log 2, where h log 2 is greater than or equal to log n factorial. H log 2 is greater than or equal to log n power, and h we take log on log to right side, that is log to n factorial, that is log, that implies h is greater than or equal to log 2 of 1 comma 2 comma 3 comma so on. That implies h is greater than or equal to log 2 log base to 1 plus log base to 2 plus log base 3 2 and plus so on till log 2 base log base to n. That implies h is greater than or equal to sigma of I is equal to 1 till n extends to n log 2 log base to I. H that implies h is greater than or equal to log 2 I minus 1 di. H is that implies h greater than or equal to log 2 I x power 0 and sigma 1 to n minus 1 to n 1 by I xi di. That implies h greater than or equal to log 2 n minus differentiation of 1 to n 1 di h greater than or equal to n log base to n minus I 1 extends to n. That implies h greater than or equal to n log to n minus plus n plus 1. Ignoring the constant terms, we get h greater than or equal to n log to log base to n. That implies h is equal to pi n log n. Comparison tree for binary search. Example: suppose we have a list of items according to the following positions: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The mid value is 1 plus 14 by 2. That implies 15 by 2 is equal to 17.5. We get 7 as integer value, and then we choose a midterm from the 1 to 6 and 8 to 11, where mid is 3, and here mid and right side we get mid is equal to 11, and left side of left subtree will get mid as 1, and right side of left will get mid as 5, and then right side of mid will get 9. The right side of right mid get 13. At last midpoint is 2, 4, 6, 8, 10, 12, 14. Thus we will consider all the midpoints, so and we will make a tree of it having stepwise midpoints. The bold letters are midpoints here. According to the midpoint, the tree will be 7. Left subtree contains 1, 3, and right subtree contains 11, and the left subtree left contains 1 comma 2, and the right side of left subtree contains 5, 4, 6, and the right side of right subtree contains 12, 13, 14, and left side of right subtree contains 8, 9, 10. Oracle and adversary argument. Another technique for obtaining lower bounds consists of making use of an oracle. Given some model of estimation such as comparison tree, the oracle tells us the outcome of each comparison. In order to derive a good lower bound, the oracle efforts its finest to cause the algorithm to work as good as it might. It does this by deciding as the outcome of the next analysis the result which matters the most work to be needed to determine the final answer, and by keeping step of the work that is finished, a worst case lower bound for the problem can be derived. State space method. The state space method is a set of rules that show the possible states and tuples that an algorithm can assume from given state of single comparison. Once the state transactions are given, it is possible to derive lower bounds by arguing that the finished state cannot be reached using any fewer transactions. Given an n distinct items, find winner and loser. aim when state changed, count it, that is the aim of state space method. In this approach, we will count the number of comparison by counting the number of changes in state. Analysis of program to find out the smallest and biggest item by using the state space method. State, it is a collection of attribute. Eighth one, this, though we sort out two types of problems, find the largest and smallest element of from an array elements. To find out the largest and second largest element from an array of an element. For the largest item, we need 7 comparisons, and what will be second largest item. Now we count those teams, those who lose the match with team A, teams B, comma D, comma E. So total number of comparisons are 7. Let n be the total number of items. Then comparisons is equal to n minus 1 to find the biggest item. Number of comparisons to find the second biggest item is equal to log 2, log base to n minus 1. In this, number of comparisons are equal to number of changes of state during the execution of algorithm. Upper bound theory. Upper bound theory says that for an arbitrary input, we can always sort in time at most u of n, how long it would take to solve a problem using one of the known algorithms with worst case input as upper bound. Improving an upper bound means finding an algorithm with better worst case performance. U of n is minimum overall known algorithms of maximum complexity. Both upper and lower bounds are minima or over the maximum complexity of input of size n. The ultimate goal is to make these two functions coincide. When this is done, the optional algorithm will have L of n is equal to U of n. According to upper bound theory, for an upper bound U of n of an algorithm, we can always solve the problem at most U of n time. Time taken by known algorithm to solve problem with worst case input gives us the upper bound. Thank you.